welcome to the second part of this contributed talk sessions. And now our first speaker is Anton. And Anton, yeah, he's sharing his slides. We can see it. Okay, can you go to the full screen?
Yes, can you hear me?
Yes, we could hear you perfectly.
Okay. Oh, okay.
Yeah, you're good to go.
Thank you, Ilya. Thank you, Francesco and Camille, for the organization of such a nice workshop. I have a honor to present the following talk: Redfield local and global quantum master equations from the viewpoint of quantum stochastic limit. Thank you, Gabriel, for mentioning the local approach. So as you see, I also will mention it. What is this talk about? We deal with open quantum systems, weak coupling limit. There are various types of quantum master equations: Redfield, non-secular Redfield, global, fully secular, Garini-Kosakovsky-Lindblad-Sudarshan equation, partially secular Redfield equation, local GKLS equation, and some other. We try to construct a unified theory. So from these many types of equations, we try to construct a unified theory based on a correct formalization of the limiting regime. And also the second small part is that quantum stochastic limits. Usually in open quantum systems, we describe the only the reduced dynamics of the system, but quantum stochastic limit is a method which allows us to describe joint dynamics of system and both, but still in an approximate way, in a weak coupling limit way, so easier than the exact dynamics. So weak coupling limits, the usual setting, for simplicity, it's not important, but for simplicity, the interaction term consists of only one such term. And if we apply usual method of derivation of master equations, for example, in work by Redfield or in the famous book by Breuer and Petruccione, then we arrive at such a Redfield equation. This is the most generic master equation for the weak coupling regime, but unfortunately, it is not of the GKLS form, and so it does not preserve positivity. This means that, in particular, we have some unphysical spectroscopic signatures, so the violation of positivity is not good in some cases. Also, since it is not of the GKLS form, the numerical Monte Carlo techniques are less efficient here. Now, from the other side, let's go to rigorous derivation. For example, by Davis. In rigorous derivation, we use the so-called Bogolyubov-Van Hove limit. So, sorry. We use Bogolyubov-Van Hove limit. So lambda, the coupling constant, tends to 0, and time tends to infinity, such that lambda squared time is a constant, tau, the rescaled time. Then, if we perform the same derivation, we arrive at such terms. And of course, in the limit of infinitesimal lambda, the terms with omega prime not equal to omega are dropped as rapidly oscillating. This is the so-called secular approximation. It has a GKLS form, so no problems with positivity. But the disadvantage that it's inadequate when some Bohr frequencies are not well separated. So some oscillations are not so rapid to be neglected. So another limit rigorously justified is the so-called local master equation. Often it's considered to be as an approximation to the global one, for example, in our work with Professor Volovich. But there is a regime where the local equation is derived rigorously. This is also a weak coupling regime, but where all system Bohr frequencies, so differences between energy levels in these equations, omega are Bohr frequencies, the differences between energy levels of the system. The system is with discrete spectrum. I forget to say about this. And when all Bohr frequencies are quadratically small, then using the same rescaling, we obtain, we arrived at the local master equation, such an equation. It's related to the so-called singular coupling limit, which is shown in a series of mathematical works and also in the book by Breuer and Trushechkin. It also has a GKLS form, but the disadvantage, as Gabriel mentioned, the application of this equation outside of this limiting regime leads to violation of the second law of thermodynamics, as was shown by Levy and Kozlov. There are some references, so there is a huge number of works about different kinds of master equations, about various solutions, about partial circular approximation, time course graining, a kind of partial circular approximation, a huge discussion about local vs global versus global master equations, and so on. So we have not a universal solution. Each equation has some drawbacks, but we have a number of heuristic solutions. My point that the reason, the main point, the non-secular limiting regimes are not fully formalized. What do I mean? If the coupling constant tends to 0, but we claim that such term is not rapidly oscillating, this means that formally the difference between Bohr frequencies is also infinitesimal. Moreover, it's proportional to lambda squared, is quadratically small, and we should explicitly take into account this in the model. All problems with positivity and so on comes from the fact that our model is not fully formalized. So our aim is a rigorous derivation based on the correct formalization of the limit. So now consider again a Hamiltonian where the system Hamiltonian is also dependent on lambda and the set. Let the Bohr frequencies can be grouped in such a way. F is a set, the set of Bohr frequencies, and they are grouped in such a way. So the differences between Bohr frequencies inside one group is proportional to lambda squared. Then we again apply Bogolyubov-Van Hove rescaling and apply standard projection operator technique and obtain the following equation, again in the Schrödinger picture and with the original time variable t. Such equation. It is of the GKLS form, and it covers all particular cases. It covers full and partial circular approximations. Full circular approximation means that that all Bohr frequencies are well separated. Partial circular approximation is a circular approximation between different groups, but not inside each group. And local master equation is also a particular case where when Bohr frequencies are all inside a single group centered around 0 Bohr frequency. So all Bohr frequencies are quadratically small. So it may be not seen from this form, but in fact, it's the most general form of master equation for the coupling limit case. And it is a GKLS form, obviously. The closest heuristic solution proposed in the literature before is the so-called partial circular approximation plus slowly varying spectral density approximation in these two works, Ptashinsky and Esposito, and Macaulay and other authors. The obtained master equation, this one, is even simpler than proposed in these works. Maybe it's an advantage, maybe it's a disadvantage. It depends on what do we want. Sometimes simplicity is good, sometimes the more detailed equation is good. But our derivation is rigorous in contrast to some heuristic propositions related to the slowly varying spectral density. And the second part, short part of the talk, that if we use the more advanced method, not a projection operator method for the derivation of quantum master equation, but more advanced quantum stochastic limit method, then positivity comes from unitarity of joint dynamics of system and reservoir. Quantum stochastic limit was described, for example, in this book by Akardy, Liu, and Volovich. Let's consider a particular case of Bath Hamiltonian, a continuum of oscillators, and a particular form of interaction term. And then if we consider again Bogolyubov-Van Hoff rescaling, then one can prove that interaction Hamiltonian tends, in some sense, it tends to the quantum white noise Hamiltonian. And then the joint unitary dynamics of a system and reservoir tends also can be approximately described as a stochastic quantum, not classically stochastic, but quantum stochastic unitary dynamics. So the exact unitary dynamics is difficult to solve, but this is approximate the dynamics of a system and bath together. But it's tractable, and the master equation for the reduced density operator of the system is a consequence of this joint dynamics. So this is a more general approach. And if everything is done correctly, then we don't care about positivity. It simply comes from the unitarity. In fact, I obtain my results, my unified master equation, at the beginning from this approach, more general, and where we don't care about positivity because our approximate dynamics is unitary, and then we can apply also the projection operator technique. So conclusions: we proposed unified, universal, rigorously derived master equation, and also I said a pair of words about quantum stochastic limit of the joint dynamics of the system and bath. And so we search for applications of quantum stochastic limit. So where one needs to know not only the reduced dynamics of the system, but also the joint dynamics of system and bath. A minute of advertisement. More detailed version of the talk I will present on our workshop, New Trends in Mathematical Physics, on 11th December. And special thanks. I would like to thank my friend and colleague Alexander Teretionkov for continuous fruitful discussions and idea exchange. Please pay attention to his recent work, also about Bogolyubov-Van Hoff limits and quantum master equations. Bogolyubov-Van Hoff limit is not just a mathematical justification. It's really an instrument which can capture some things not captured by less rigorous methods. And also special thanks to Jeannet, Anders, Louis Correa, and Marco Cataneo for exciting and inspiring discussions on quantum thermodynamics conference recent. In fact, this work was inspired by a fantastic discussion on the QTD. And for some references. Thank you, Marco. And thanks all of you for attention.
Thank you very much, Anton, for very nice talk and for perfectly keeping to the time. Okay, so before people can figure out and ask some questions while they're thinking, can I ask a question? You present a very nice and systematic approach how to obtain a very consistent equation. But do you have an example where you would have this small parameter dependence inside of the Hamiltonian of the system? Like, because usually you have it like inside of the, for example, So how this dependence, how the same parameter lambda is sitting in the system and in the system bath interactions? Do you have some physical examples?
Yes, I have. These results are, as I said, are very preliminary because they are inspired by very recent discussion on a quantum thermodynamics conference. But yes, so this is, I agree, this is a very simplified situation. I considered one physical example yet, two qubits coupled to reservoirs where with small interaction proportional to lambda. This is what I considered. So yes, I have some particular physical cases, and the generalization of such a simple picture is not difficult in fact.
Okay. Very good. Oh, there is a question in Q&A from Janet. Thank you, Anton. Very nice talk. Do you have any specific example of difference between your local global equation? Ilya asked the same question. Okay, so that probably would be of interest. So it's clearly so that if you have an example where you have the transitions between this sort of equation, that would be nice. And there is a question from Marco. Thank you very much for these groundbreaking results, Anton. Could you give an intuition about form of your identified master equation? For instance, in the standard structure of the master equation, meaning by Redfield or Breuer-Petruccioni, which is the form of the decay rates and the jump operators?
So intuition about the form of the unified master equation and
I can allow Marco to
okay, I understand. Yes, if the question is about decay rates and jump operators, this equation also, of course, can be these terms can be divided by a lamp shift Hamiltonian and dissipative part. If the question is about this, or what do you mean?
Marco, you can unmute yourself and
do I answer the question? Huh? Sorry?
I allowed Marco to ask his question, to specify his question if he wants to. Okay, if you don't want to,
yes, please, Marco. Marco has written, I don't have a microphone now. I was just asking for a formula for the decay rates and jump operators. I think the formula is more or less the same, because gamma, you see here gamma of omega, gamma of Bohr frequency. So more or less the same like in a Redfield equation, but the difference is that we plug here not the Bohr frequency, but center of the block of Bohr frequencies. This is something similar what these guys do, in fact, but now rigorously derived.
Okay, great. I don't see any more questions or the raised hands. I think we can thank Anton. Thank you very much.
And thank you very much for attention.
And